The beginning of the world, and with it the beginning of our own life story, dates back 13.8 billion years. The Big Bang is the origin of our universe. It is the cradle of humankind, and it is also our starting point in our quest to discover how the universe works, how it is developing, and above all, how it came into being. To date, we only know of one celestial body on which life exists, our planet Earth. Yet the building blocks of life exist everywhere in the universe.
Woher kommen wir? Wer sind wir? Und
Where do we
wohin
come
gehen wir?
from?
Das ist
What
der
are
Titel
we?
eines allegorischen
Where are we
Gemäldes
going?
von Paul Gauguin.
This is the title of a
Und Sie werden
painting
sich
by
sicherlich
Paul
schon mal
Gauguin.
gefragt haben, hat mein
And you might have
Dasein
asked
wirklich
yourself,
eine Bedeutung
am I here
oder
for a reason or merely by chance?
Nun, Fakt ist,
The fact is,
das
the universe can produce intelligent life.
bewusstes Leben hervorbringt.
We are the living
Wir
proof.
sind der beste Beweis. Aber heißt
But
das,
does that mean that life is inevitable?
häufig entsteht
Anywhere?
überall,
On any
irgendwo,
planet?
auf irgendeinem Planeten? Nun, dort
Well,
draußen gibt's
there are
Milliarden
billions of
von
planets
Planeten.
out there.
Und
And
wenn
if
dem
that
so
was the
wäre,
case,
dann
then
wären
we
wir
would
mit
certainly
Sicherheit
not be
nicht
alone
allein
in the
im
universe.
Universum. Aber
But is that the
das so?
case? To
Um
find an
Antwort auf
answer to
diese
this
Frage zu
question,
bekommen,
we have
müssen
to
wir
look back
zurückblicken
to
auf
the
den
origin of
Ursprung
our life,
unseres Lebens,
but also to
aber
the
darüber
origin of
hinaus
our
auch
entire
auf den
universe.
Ursprung des gesamten Universums.
What is life? And why isn't the universe teeming with it? We are seeking the blueprint for the grand scheme. And although new insights are being gained at ever shorter intervals, our understanding of the universe is still far from complete. To find our origins, we need to understand the small and large correlations between the formation of galaxies, stars, and planetary systems. Cosmology and cosmogony, theories about the universe and about the origin of the world, intrigue scientists and philosophers alike. Whether the emergence of life in the universe is an incredible coincidence or inevitable is a fundamental question for humankind.
People always want to know, why am I here? What is the meaning of life? But the meaning of life is not something that can be explained with physics. Still, the question is of great significance. And that's where the limitations of physics lie. That's where philosophy and theology come in. And what is always sorely missing is a dialogue between these disciplines, away from physics and towards the question of what the whole thing has to do with us as human beings.
There is still no definite answer as to the question of how biological life as we know it really originates. How life was able to form from inanimate matter is one of the greatest, perhaps even the greatest mystery of the world. The path from rock to human is full of unsolved enigmas. The phenomenon of life is complex and difficult to grasp, starting with the very question of what actually constitutes life.
Es gibt tatsächlich keine
There really is no conclusive, simple definition. It is really a list of certain criteria, and the list does not claim to be exhaustive. The definition starts with metabolism. Then comes the ability to multiply, to replicate, to reproduce over and over again. Life has an information unit, and life can evolve. That means it is able to improve itself.
To this day, we only know life as it exists on Earth. There are 118 chemical elements in the periodic table. Only 6 of these form the building blocks for our existence: hydrogen, nitrogen, oxygen, phosphorus, sulfur, and most notably, carbon. These building blocks of life apparently exist throughout the universe.
We have over 100 billion planetary systems in our Milky Way. There are more than 100 billion Milky Ways. All that effort, and suddenly life exists here on Earth for just 4 billion years? Then the sun explodes and it's over? That does not make sense to me. So why the vast effort? That's why I think there is life everywhere and we just have to find it.
Our universe was created in a Big Bang, the Big Bang. Marking the time when everything began, this primordial explosion defies any physical description. Researchers see it as the result of an unknown cause, or as pure coincidence. They cannot unravel the actual moment of the Big Bang using the laws of physics. Scientists can only describe how the universe evolved after the Big Bang. The Big Bang not only created all matter in the universe, but also space and time itself. To ask what came before it misses the point. There was no place or time preceding it.
With the Big Bang, our universe expanded in what is known as inflation, so that every tiny area of space, the size of a grain of sand, became an area the size of our Milky Way. And it was at this stage that the first elementary particles appeared, namely quarks and electrons. However, it only took a millionth of a second for these elementary particles to form the first nuclear particles, the so-called neutrons and protons. After about 100 seconds, the first nuclei were formed from these nuclear particles, and over 99% of them were hydrogen and a little helium. However, in the form of red-hot plasma. This plasma continued to expand and cool down. After around 380,000 years, it reached a temperature of 3,000 degrees Celsius. And this suddenly produced a neutral gas, which was no longer red-hot at all. It was pitch black back then, the beginning of the so-called Dark Ages.
The Dark Ages, a world of total darkness. Neither stars nor other sources of light existed in the newborn universe. In the first phase, lasting only a few minutes, the nuclei of the two lightest elements were formed, hydrogen and helium, the primordial gas. All the chemical elements that make up stars, galaxies, planets, and all organisms, including us humans, emerged much later.
The most exciting question off the bat is, was the possibility of life originating in our universe already embedded in the blueprint of the universe? Was it possible to predict that life could actually emerge just by looking at the blueprint of the Big Bang and what the Big Bang had already produced? Or is life something of an afterthought of the universe?
The first galaxies and stars appeared a few 100 million years after the Big Bang, massive celestial bodies with a short lifespan. In the hot cores of the stars, hydrogen and helium fused to form heavier elements, including iron. At the end of their lives, supernovae produce all known elements up to uranium in massive explosions.
We believe that very small galaxies were formed first, small clusters of relatively few stars. And these galaxies then grew rapidly, producing more and more stars. As soon as the first stars created heavy elements, this completely changed how subsequent generations of stars would form.
Looking up into the night sky, it seems as if the stars and galaxies are randomly spread out. Astronomers, however, identify patterns, a large-scale structure consisting of galaxies and gas dominated by dark matter, which makes up the majority of the mass in the universe. Cosmologists call this structure the cosmic web.
It's a very delicately spun web comprising filaments of matter, strands that intersect at certain points. And there's a lot of matter at the intersections. We call them knots. At the largest of these knots, we find clusters of galaxies, the largest systems we know in the universe. And these galaxy clusters and groups of galaxies are connected by filaments, and most of these consist of dark matter.
Materiebrücken, die aus dunkler Materie bestehen.
The cosmic web consists of interconnected threads of galaxy clusters extending across the entire universe. They are separated from each other by huge empty spaces, known as voids. With today's simulations of cosmic evolution, it is possible to provide supporting evidence for theories of galaxy formation.
This number crunching is of major importance today in cosmological research and in extragalactic astrophysics. You can see how rich the data is that supercomputers generate. With their help, we can study the universe in all its aspects, including time.
In the universe, major events occur on timescales that are beyond any human imagination. The merging of two galaxies, for example, can take 2 billion years.
I can produce a video simulation on the computer, condensing these 2 billion years into a 1-minute time-lapse. That's an incredibly powerful tool for theoretical astrophysicists.
Clusters of galaxies and gas extend across the entire universe, separated by vast spaces of apparent emptiness. Galaxies form groups, clusters, and superclusters. The latter extend over hundreds of millions of light years and contain billions of galaxies. These galaxies are interspersed with molecular clouds, nebulae, the remnants of explosions of dying stars, which are also the birthplaces of new stars. The elements can travel through space as dust for millions and billions of years until new stars are formed from them. The birth of a star with a planetary system lays the ground for life, the first step followed by countless others.
If you look at the various physical processes, they are aligned in just the right way for life to develop. If you change the natural constants ever so slightly, it won't work. If they didn't have dark matter, no structure would have been created. So they need the dark matter for the neutrinos alone. You might ask, why do you need these ghost particles? But we know now that if neutrinos didn't exist, no star would be able to explode, because the neutrinos drive this explosion. We had always neglected this aspect before. And if there are no stars, there is no stardust. So every little building block that we find plays a role in creating the possibility of life in the overall scheme of things.
The force of a supernova, the explosion of a massive star, is so great that some of the matter is hurled out of the parent galaxy, floating through space. Matter that can form the basis of planetary life.
If you observe these exploding massive stars, the supernova, and then analyze the light, you can see exactly the signatures of the elements that make up life: carbon, nitrogen, oxygen. The fundamental building blocks of life can be found in them, and in exactly the right quantity and frequency needed for life. You see CNO and hydrogen H from the Big Bang, and HCNO. These are the fundamental building blocks of human beings. Then a little phosphorus is added to create DNA, but the main building blocks are found in the exploding stars and in the Big Bang. We are the combination of the Big Bang and stardust.
The first generation of stars perished in supernova explosions. A second generation of stars formed from the remnants, which can still be observed today. The explosion of these stars then produced a third generation, including our Sun.
Supernova-Explosionen erzeugen neue Sterne.
Supernova explosions create new stars, and this image is intended to show us exactly how this happens. What we see is a supernova explosion at an advanced stage. During the explosion, the star expels its fused matter at almost the speed of light. This matter collides with what is known as interstellar matter, mainly hydrogen gas, pushing it forward. You can see this particularly well up here. The front is pushed further and further outwards, and the hydrogen accumulates in the shock front. The shock front becomes denser and denser until it finally collapses under its own weight. At the shock front, new stars are formed in clumps. How do we know all this? Because this collapse produces infrared radiation. We can't see it here on Earth because the atmosphere absorbs the infrared radiation. That's what space telescopes are for. The Hubble telescope was the first to study such effects, and the James Webb telescope should show all this even more beautifully.
The James Webb Space Telescope marks a new chapter in our exploration of the universe. Operating in the near and mid-infrared range, it will allow researchers to look deeper into space than ever before. In the so-called Pillars of Creation, a formation of gas and dust in the Eagle Nebula, 6,500 light-years away, thousands and thousands of stars are forming. James Webb's infrared cameras provide an astonishingly precise view of the places where stars are formed. By observing such areas, we also learn more about our own origins.
We've always wanted to know where we come from. That's the origin of many religions. All these big questions. Where do we come from as individuals? What is our role in this universe? And of course, astrophysicists are looking for answers. Then we begin to see how complex the universe is, how many billions of stars there are in our galaxy, how many galaxies there are in total. You start to feel a certain humility in the face of the universe. But what we really want to know, of course, is what happened physically and chemically. How did the Earth, for example, come into being here after so many billions of years?
The James Webb Space Telescope will be the new workhorse of astronomy for years to come. Like the Hubble telescope, James Webb will deliver completely new findings. Its data will be combined with that of other instruments, such as X-ray telescopes.
You can observe different physical processes at every wavelength. Using stars as an example, the X-ray data allows us to characterize how active the stars are. Young active stars emit X-rays. So if we're interested in how planetary atmospheres develop, we want to know what properties the stars in the center have. The same applies to galaxies. X-rays come from the highly energetic processes in their center. So if you want to find out about black holes, you can find this easily in the X-ray range. And if you observe the galaxies all around, you're more likely to go into the infrared spectrum.
Of course, the James Webb Space Telescope is also intended to focus on distant planets. In the search for life outside our solar system, researchers are particularly interested in celestial objects similar to Earth.
For centuries, astronomers had suspected that there must be exoplanets out there. But it was not until the early 1990s that an exoplanet was actually detected for the first time. And not all exoplanets are the same. There are huge gas planets out there, which were the first to be discovered, similar to Jupiter. That's not what we're looking for. We're on the lookout for Earth-like planets. Can life develop on Earth-like planets? Well, it requires certain conditions. First of all, we need a star that produces a constant light intensity so that climatic conditions become consistent. At the same time, a planet must orbit within the so-called habitable zone. Only then the constant climatic conditions can persist. What's more, the planet cannot be smaller than about half the size of the Earth. Why? Because then it can no longer support an atmosphere, as there is not enough gravity and no hot core generating a magnetic field to protect the atmosphere from the solar wind. Today we know a planet that can support life must be about the same size as Earth, plus or minus 50%.
The first discovery of an extrasolar planet in the early 1990s ushered science into a new era. What had long been suspected is now a certainty. Planetary systems are the rule in the universe and not the exception. With the James Webb Telescope, researchers can now take a closer look at alien worlds.
What's really exciting is that we can now characterize the exoplanet's atmospheres much more precisely using spectroscopy. We can do this for those that we can image directly, recording light spectra. But we can also apply this method to those that have been discovered through transit observations. On the one hand, we can analyze giant planets like Jupiter, some of which are extremely hot. But we also analyze planets that are similar to Earth.
Most of the exoplanets discovered are gas giants, such as Jupiter or Saturn. However, researchers repeatedly find rocky planets as well. As many as 7 Earth-like planets orbit the dwarf star TRAPPIST-1, some of them in the habitable zone, the area where water may be liquid. This discovery is a sensation. The James Webb Space Telescope has taken a closer look at some of these planets. Only 40 light-years away, the star system is the most promising so far in the search for extraterrestrial life. James Webb's keen eye is providing researchers with new insights.
The particularly exciting thing was to carry out observations for planets in a system called TRAPPIST-1, named after the famous Belgian beer, because Belgian astronomers built the instrument. And there's one star that has a total of 7 planets in its orbit, some of them even in the zone where liquid water could exist. Initial observations have shown, however, that they don't have dense atmospheres that could consist of CO2, like the Earth's early atmosphere.
This diminishes the probability that traces of biological origin can be found in the TRAPPIST system. There are still many unknowns about the origin of life, even if science does know which building blocks to look for.
The key question is, what kind of matter can produce life? And of course, we first assume that it is mainly carbon-based molecules, large carbon-based molecules, as we find them on Earth. As atoms go, carbon is a pretty special atom. It has the ability to form bonds that other atoms do not have. That's why we're very impressed by carbon and its compounds. So when we look for life in the universe, we're actually looking for carbon compounds, like those we find on Earth. So we're basically looking for molecules that represent what life on Earth is all about. While it is true there could be completely different forms of life, but because we don't know them, we're looking for what we do know.
A combination of methane and oxygen, or ozone, could indicate life. However, it is still not possible to say with certainty which traces in the atmosphere of an extrasolar planet are the result of biological processes. The only model for understanding the atmospheres of young planets is our knowledge of the early Earth.
The next big step will be to observe Earth-like planets around Sun-like stars. But we don't know of any yet. Although we know of 5,000 planets in total, we haven't found a single Earth-like planet around another sun in our Milky Way system. This is because it's much more difficult to discover such planets around Sun-like stars. That's the goal for the next 20 years.
A second Earth, the holy grail of astronomy. Today, science assumes that life on Earth began around 4 billion years ago, presumably in small, enclosed areas in which biomolecules were able to react with each other. However, the distribution of land and water on the early Earth is just as unknown as the temperature at that time, which is important for chemical processes.
We now know that 1 in 50 stars has at least one planet capable of producing life. That makes around 5 billion potential planets in our Milky Way alone. The only question is, how likely is it that life will actually develop on a planet? Let's take a look at the premises for biological life. We need carbon, nitrogen, lots of water, a few minerals such as calcium, phosphorus, and so on, and lots of energy to really develop an initial cell. But all this is available in every corner of our universe. Does that mean that life is created necessarily? We don't know, because we only know of one case, the one on our Earth. And 4 billion years ago, when that happened, we weren't there. In other words, evolutionary biologists are still completely in the dark.
Researchers are still unable to explain with certainty the origin of life on the young Earth. How complex biological life was able to develop from inanimate matter around 600 million years after the formation of our planet is a mystery. Scientists suspect that life evolved from a kind of primordial cell.
Cells, as we find them in nature today, are considered to be living matter. Now, the question is, how did these molecules manage to form cells? This is the transition that it comes down to, the transition from inanimate to animate nature.
Life is based on chemical reactions that can only take place under one condition. Molecules must be close enough to each other to react. Researchers do not yet understand how simple molecules started to form the large, information-bearing and self-replicating building blocks of organisms. It seems certain that life began in water, perhaps in the Earth's interior. To this day, researchers are finding creatures that can exist even under extreme conditions. But the answers to fundamental questions, such as how the first DNA molecules were able to form, are still murky.
We only know one form of life. It is based on DNA. And DNA is something that does not arise naturally. If you take a test tube and fill it with all the building blocks, all the atoms you need, and stir them up, no DNA will form. And that's the problem. DNA is also extremely fragile. It breaks down again very quickly. So how was the original building block created? We don't know that yet.
Large organic molecules can be found everywhere in the universe. Researchers have also detected these potential seeds of life in dust particles from which planets are formed. The seed of life might already have been in the dead matter from which our planet Earth was formed. Around 4 billion years ago, the first precursors of life began to emerge on our planet. Biomolecules, the molecules of life, were built from the elements carbon, hydrogen, phosphorus, and sulfur. In 1953, 2 researchers attempted to recreate the origin of life. In a test tube, they wanted to create the same conditions that prevailed on early Earth. The fact that complex building blocks of life can be created from simple molecules by adding energy was first demonstrated by the young chemist Stanley Miller, who worked in the laboratory of Nobel Prize laureate Harold Urey. The Miller-Urey experiment is seen as proof that biomolecules can be produced easily from inorganic substances. However, the researchers were unable to reproduce the generation of life.
The definition of life is very strongly linked to the definition of the cell. Without a cell, there's no life, and every cell emerges from another cell. Of course, it's a bit like the chicken and the egg. At some point, there must have been a first cell that did not emerge from another cell. And that cell, which did not emerge from another cell, is then, by definition, the original cell. The first one that was able to give rise to other cells from itself.
The first living cells may have formed around 4 billion years ago in deep fissures in the continental crust, tectonic fracture zones connecting the Earth's mantle with the Earth's surface, in which gases and liquids circulate. Hydrothermal conditions prevail in these fissures. Due to the high pressure, water can still be liquid at well over 100 degrees Celsius. Therefore, it contains many dissolved gases and minerals, favorable conditions for life to develop. Crater lakes and hot springs are also among the places where life could have formed. Life likes imbalance. For example, the change between warm and cold. Cells, as we find them in nature today, are considered living matter. But it is still unclear how the first biomolecules managed to form cells.
How do you get from that complex biomolecule, which is already much more complex than anything inorganic, to the smallest cell? That is really a dramatic gap, and we're trying to close it.
Solving this mystery means finding the leap from inanimate to animate nature. Our planet has changed considerably since the formation of the first cells. This constant change has destroyed, or at least blurred, the traces of any primordial cells. So scientists are also searching the universe for the basic building blocks of life, especially in regions where planets can form. With the James Webb Space Telescope, researchers have observed Chameleon 1, an ice cloud about 600 light-years away. Its molecules could eventually wind up in future planets. The observations could lead to new insights about the origin of complex molecules, the first precursors of life.
Man glaubt, dass der nächste Planet, der überhaupt Leben tragen kann, ungefähr 30 Lichtjahre.
Scientists believe the nearest planet that can support life is about 30 light-years away, in any direction. 30 light-years doesn't sound like much, but if we really wanted to fly there with future technology, it would take us more than 1,000 years. And we would need the right spaceships, giant interstellar arcs in the form of rotating tubes, creating artificial gravity through rotation. Another question is, can humankind reproduce there, and then later on the newly found planet in the same way as on Earth? We don't know. Research hasn't advanced that far yet.
The human organism is not designed to travel to worlds outside our solar system. Its lifespan is just too short. Mars, however, lies seemingly within reach. Scientists suspect that our red neighbor could once have supported life. Its landscape indicates that once there was liquid water on its surface. And so the planet has long been the focus of the search for extraterrestrial life.
Der Mars hat die Fantasie der Menschen angeregt, weil so ähnlich ist wie die
Mars
Erde.
has captured people's imagination because it's so similar to Earth. It's still relatively close to the Earth. It's not too far away from the Sun, so that it would be completely cold and dead. It's not too close to the Sun, so that it's too hot. It's at a distance where life could still exist. And that actually makes it attractive, because you could assume that Mars had water hundreds of millions of years ago. There's substantial evidence that Mars was covered with oceans. So if there were temperatures at which water was liquid, the basis for life existed. And that is of interest, of course. And if there was water on Mars for a long time, then microorganisms could have formed.
Humankind wants to conquer Mars, to set foot on the neighboring planet, to study it even more closely. Permanent research stations or even a colonization of Mars are visions that kindle people's imaginations. At the same time, the challenge of landing humans on the red planet and feeding them on site presents engineers and scientists with many problems that have not yet been solved. Nonetheless, reaching Mars appears to be technically feasible. However, humans will probably never be able to travel to more distant celestial bodies.
If you wanted to go even further, for example, to Saturn's moon Titan, a moon with a dense atmosphere, that would be an extremely exciting object to fly to. In this case, we're talking about missions lasting perhaps 20 or 25 years. That's a challenge, and you won't be able to shorten these missions. So you'd have to find someone who's prepared to give a quarter of their life to this cause. What's more, you would also have to guarantee full service for those 25 years, including medical care. We're talking about massive spaceships that would have to be built, which we can't even dream of at the moment.
Traveling to the edge of our solar system and beyond is pure utopia. The distances are immeasurable and beyond any human scale. The Earth's closest star is Proxima Centauri, 4.2 light-years away. With today's propulsion technology, the journey would take more than 6,000 years.
First of all, it has to be said that outer space is frustratingly vast. It's so frustratingly vast that you almost lose the desire to even think about flying to another star. Again, the serious challenge here is the physics. There's the so-called rocket equation. It tells us that we can't travel much faster than with our current rockets. It's just not possible, according to the laws of physics. There's a physical limit. In other words, if we wanted to fly to other stars, then we would need huge spaceships to simulate a second Earth. Many generations would have to live there in order to get to another star. Something like that is conceivable, but not realistic.
Even just 6-month or year-long stints on the International Space Station show that the human body is not yet cut out to live permanently outside its planet. The origin of man lies in the Big Bang, the beginning of the universe. The Earth then gave rise to humans, and they seem to be bound to it.
Es gäbe natürlich die Möglichkeit, einfach das Leben der Menschen zu verlängern.
There's the possibility of extending people's lives. Assuming that a journey to the nearest star takes 10,000 years, you could try to imagine a person living for 10,000 years. I think it's difficult to imagine that from a medical point of view, because many things indicate that the maximum lifespan of a human being would be around 150 years. Then, of course, you might think, maybe at some point, we will be able to simply make the transition from carbon-based life to life based on silicon.
zum Leben.
Recently, artificial intelligence is developing very fast. And if you could build a computer with a consciousness and even an identity of its own, such a machine would no longer be limited by human lifespans. It could certainly travel anywhere for 10,000 years and would have a completely different sense of time. And that could be a way to bridge great distances.
So kann man sich vorstellen, dass die Entfernung überbrückt wird.
Earth. A huge, lonely spaceship in the broad expanse of the universe. Our planet has all the prerequisites that are necessary for life to develop and exist. Water, an atmosphere, a magnetic field to protect us from radiation, a moon to stabilize our climate. Evolution has adapted humans perfectly to their environment. And so, our home planet is also a kind of prison. We can take short trips into space, but we cannot leave our solar system to search for alien life. The fundamental questions about our origins and whether we are alone can only be investigated using probes and telescopes.
Some astrobiologists suggest that we don't need to look that far out. Life already exists here in our planetary system, namely on the moons of Saturn and Jupiter. Why? Well, we know that there are huge oceans there, liquid water, and that's the perfect prerequisite for life beyond Earth.
The icy moons orbiting the gas giants Jupiter and Saturn probably have the necessary conditions for life to emerge. Researchers suspect oceans of liquid water underneath their frozen surfaces. One candidate is Saturn's moon Enceladus. The brilliant white moon has already been visited by the Cassini space probe. It owes its brightness to a constantly renewing layer of ice and snow. On its southern hemisphere, there are fissures and cracks from which water emerges and shoots into space in huge jets. Some of it trickles back onto the surface of the moon as fresh snow.
We assume that liquid water is an ideal medium to enable life and to protect it from outer space. The moons are just as old as the Earth, 4.5 billion years. Given all that time, something complex could possibly have developed on them, if you assume that water is a fundamental substance needed for life.
For a long time, scientists focused their search on our neighboring planets, Mars and Venus. But perhaps it is the distant moons in our solar system where researchers will discover extraterrestrial life.
This is a new idea. And it's interesting because it significantly expands the habitable zone. All icy moons, no matter where they are located, could generate life, contrary to what has been assumed so far.
Another fascinating world is Saturn's moon Titan, alien and yet strangely familiar. It has an atmosphere and landscapes on its surface that are reminiscent of Earth. A cloudy sky, barren plains, mountains, rivers, and lakes. However, it is minus 180 degrees Celsius there. The lakes are not filled with water, but with liquid methane. The atmosphere is a nitrogen atmosphere with clouds of methane. Titan has already received a visitor from Earth. In 2004, the European space probe Huygens landed on its surface. Another European mission is on its way to Jupiter, the largest planet in our solar system. JUICE, the Jupiter Icy Moons Explorer, is bound to systematically explore Jupiter and its satellites. More than 60 moons orbit the gas giant.
The JUICE probe will soon be visiting and investigating 3 of them. We want to see whether these icy moons could harbor life. JUICE won't be looking for living organisms because its instruments aren't suitable for that. But it will examine the moons to see whether life is or could have been possible there.
Allumage Vulcain. Allumage AP, décollage.
On April 14, 2023, the European research mission JUICE was launched into space from the Kourou spaceport in French Guiana. The probe will travel to Jupiter for around 8 years. Once there, it will focus on the 3 moons, Callisto, Europa, and Ganymede. This mission is also about the search for life in our solar system. The mission is one of the most challenging that European space travel has ever undertaken.
The satellite has 10 different instruments on board to study various aspects of Jupiter and its moons. And those are the atmosphere, the magnetic field, the oceans. This means looking deep inside the moons, under the surface, to better understand their structure.
The probe is designed to explore unknown worlds. JUICE will provide more information about the oceans that may be hidden on the icy moons and detect possible underground water deposits. The probe will also map the surfaces of the moons and examine the objects deep inside their cores. The researchers want to know what the moons are composed of and how they have changed over time. In addition, their wafer-thin atmospheres, the so-called exospheres, are to be analyzed during the mission. Ganymede is of particular interest, as it is the only moon in our solar system that has its own magnetic field.
The fact that it has a magnetic field is extremely exciting. It could indicate that the probability of finding or being able to find traces of life is greater there. And that is why we are so interested in Ganymede, the largest of Jupiter's moons.
The visit will be the highlight of the mission. JUICE will be the first space probe ever to enter orbit around a moon of another planet. In Ganymede's orbit, the probe will study its magnetosphere and inner magnetic field and collect data about the moon's surface and the ocean hidden inside it. At the end of the journey, gravity will mean the end of the probe. It will crash into the surface of Ganymede. The JUICE mission is one of many research projects aimed at investigating the possibility of the origin of extraterrestrial life. The scientists want to find clues that will lead them to an understanding of our own existence, the origin of our life, how it could come about, and whether other life can be found in the depths of space.
How did the first cell emerge from inanimate matter, and how did higher life develop from it? All this is still a mystery to us. What we do know is that it's very unlikely. However, we don't know just exactly how unlikely it is, because that determines whether we are alone in our Milky Way. Maybe we are, and maybe we're not. But one thing is certain, even if it were extremely unlikely, in a practically infinitely large universe, there would have to be other civilizations. Will we ever meet them, or at least be able to communicate with them? Never. Why? The distances are too great. It would be tens of thousands of light years within our Milky Way. And if we wanted to communicate with other galaxies, it would be many hundreds of millions of light years. We cannot communicate like that, which means we're alone, even if we're not.
Life can adapt to extreme conditions. But that does not mean that life will necessarily develop under these extreme conditions. To date, we only know of one example of life on our planet, based on cells and DNA. We do not know how it originated, and it is still a mystery whether this kind of life is just one possible version in the universe or whether it is unique. However, it is certain that the building blocks of life can be found throughout the universe, and they can be traced back to the Big Bang, the origin of all existence, and thus also the origin of our life.